would benefit from. I'm used to 75-minute classes. I think that's an amazing amount of time where we can actually work through things and ask a lot of questions and be more relaxed. But because we have 50 minutes at a time, it's going to be a little more, if there are specific questions, just come see me after class or during office hours, which I will announce at noon today, I think, is when I'll make a decision based off the doodle poll if I get a few more responses. All right, so for today, I want you to be able to use logic to determine the relative abundance of isotopes. Not just calculate it, but also calculate the average atomic mass of an element when given isotopes and their abundances. That's what we're moving towards, and we'll probably do a bit more of that on Wednesday as well. And then this is one of the muddiest points that I saw a lot of. Convert between mass and AMU and grams for any element that you are going to encounter. So to start this out, let's all get on the same page. I'm going to collect your homework in a couple of minutes. But go ahead and click in your response here.
It's not adding up? Like the data.
I would hit refresh on this one. Maybe your phone's refreshing quicker.
Does that mean that you don't know who I am?
Did you log in?
Yes.
Should. I'm not sure. I'll check that out after class. I think you should have your information there. A couple more seconds and I'm closing out.
Does answer received mean it has it?
Answer received means that it submitted your answer. Yeah. All right, 47 people today. Does that sound right? Okay, make sure to click on it. Remember, you have to answer 75% of the questions for the day to get credit for participation. So that means that if you're sitting back and kind of just waiting for others to answer and see what they say, that's not how this works. 54. All right, we're going to close out. And I'm very curious to see. All right. 96% of people say A. Where do you get that information from? Can I get lots of hand raised today, lots of different voices? Angel?
AMU stands for atomic mass.
Great. And so mass is in the name, so it's about how heavy things are. This is usually one of the muddiest points, the sticking points for students that they don't quite realize as you're learning to work with atomic mass units, is that's just a measurement of weight. Is it a heavy weight or a light weight? Extremely light. How light?
Oh, like point. You need like 10 to the 24 just to make a single gram if you're talking about.
So how much does a gram weigh? How many grams do you think this pencil weighs?
Oh, I bet that's at least 50.
Let's do hand raising today, if we can. So, yeah, maybe 10 grams, that kind of scale, right? So if we think about the mass of 1 AMU, if we get a hand raised for what is 1 AMU, what weighs 1 AMU? Love? A hydrogen atom, in certain cases, yes. More specifically? Kayla?
That wasn't in here.
Oh, it wasn't? That was just a pencil up? Savannah?
1 AMU is 1.6606 times 10 to the negative 24 grams.
Great. And so what weighs that amount? What is one thing that weighs exactly that amount? I can't see your name. Savannah? Also Savannah. 1 proton. What else weighs exactly 1 AMU? A neutron. Okay, when I say exactly, it's a little bit off. But your book goes into some detail as to why that's a little bit off. We're not going to be spending class time on that. It has to do with Einstein's equation. Yeah, and the amount of time we have in class today, that's not a focal point. But if we understand that 1 proton weighs 1 AMU, we can start to picture how small that mass is. And I want you with that picture in your mind. And so this is a conversion factor that we're going to be using. 1 AMU equals 1.6606 times 10 to the negative 24th grams. And so this means that you have 23 zeros before that 1. If you're not comfortable with scientific notation, we're going to be using it a lot in this class. And scientific notation is times 10 to tell us how big or how small things are. So there's another resource that I have linked from our Blackboard page. And I think it's under resources right here, and it's CHEM1402. I can't remember if I mentioned this last week. And it's killing me how I can't see my mouse. Okay. So Chem Tours is a set of interactive tools that will guide you through kind of an interactive lecture, but it shows you based on color. So like sig figs, if you're not quite comfortable with sig figs, click on that. It launches a tutorial where it highlights things in colors. It tests you then. It allows you to test yourself a couple times. There's one on scientific notation, one on dimensional analysis, and one on temperature conversions. So if these are things you struggle with at all, first thing is you need to identify that's something that you're not comfortable with using. If you don't identify it, then you're not going to address it. Once you identify it, this is one of the set of tools. Come to office hours, work with the tutors, do whatever you want to make sure that those things that are not part of the course, that are fundamentals you need to succeed in this course, that you feel very comfortable utilizing those tools. The other one that someone mentioned earlier was prefixes. So the metric prefixes, kilo, milli, nano, pico, all those kinds of things. Those are also foundational skills that we'll need you to utilize in this class. All right. So this is not the way I wanted you to do it. We're going to do these as a set of... You have already worked through these problems, correct? These are the homework problems. So this is exercises, starting exercise 2. So everyone's supposed to open this page. An exercise, that's the ones that are the second half. They're after the table. Is the first one about a carbon atom or a hydrogen atom? Okay, so I want you to compare with your neighbor how you set up this problem. Spend 30 seconds, compare with the neighbor how you set up this problem. What did you do? What did you write down? How did you solve it? What did you guys do? What are you missing?
This one right here.
Can I see hands raised? Did anyone use unit conversion to solve this problem? Yes! We have a quarter of the class who use unit conversion. These are the types of problems that we studied unit conversion for. So can I get someone to raise a hand and volunteer to say, how would we start doing unit conversion? What would be the first thing we'd write down for this problem? Matthew? Oh, sorry, Josh.
As one atom.
Almost. What do we have to do? Be more specific, Amber.
We start with one, the weight of hydrogen, so 1.08.
Not quite. Logan?
Start off with the 12 AMU that given structure.
Well, hold on. So you're thinking about carbon. So we want to build off what Josh said, but there's a slight additional piece of information we need. Ruby? One atom of hydrogen. Not quite. One little more piece of information we need. H1. Okay? If this was deuterium, if it had a 2 there, this would be a different set of conversion factors that we're going to use. So we need to be really specific that we identify what's our starting quantity. It's saying what is the mass of one 1H atom. So our starting quantity is 1H atom. We're going to write that over 1. And then, what conversion factors do we use? What's a conversion factor we can use to go from the number of hydrogen atoms, 1H atoms, to the mass in grams? Sarah? We're not quite there yet. That is one way you could do it. Go ahead, Trey.
You just do that one hydrogen atom and it's equal to
1.0078 AMU is the mass of 1. I guess we don't really need to say. We can say every 1H atom weighs 1.0078 AMU. What did this conversion allow us to go from and to? What units did we start with? What units are we going to end with here? Hand raised again. Josh?
We're going to start with that, and we're going to end with grams.
Not quite for this calculation we've done.
Oh, this one.
Yeah, so far what we've done. Okay? And I would even tweak it a little, and I would say we start with the number of atoms. Because we're specifying. Remember that last question? Is it mass, length, volume, number of them? So we want to start by saying we know how many atoms we have. This is a conversion factor that allows us to go from how many to how heavy, or mass, in the unit of AMU. Avery?
So if we just went right from what the answer of that was and then did the conversion from there, would there be any point deductions for that?
So let's complete this question. I just wanted to stop right there and say, if we stopped or we've only done one step so far, that one step has taken something from the number of them to how heavy they are in AMU. That doesn't answer the question. So then what do we need to do to go from how heavy they are in AMU to how heavy they are in grams? Can I get a new voice? Who hasn't talked yet? Kevin.
Use the conversion factor of 1 AMU equals 1.6606 times 10 to the negative 24 grams. Wouldn't that be the other way around?
So I always write it out, and then I see, is this right, is this wrong? So if you're not sure how to use each conversion factor, don't feel bad just writing it out, just do it in pencil. Okay, so if we try to do this, we look at what units we converted from the number of 1H atoms to AMU, but then we can't convert from AMU to grams because this is flipped. So then we go ahead and we rewrite that conversion factor. So 1 AMU is what we're converting from. And we're converting to grams. And then our final unit is, only have the unit of grams left, and we have some number there. Okay, I'm not too interested in the number. This is about the process right now, what we're talking about. So you might have come up with the answer on your own. You might have used a molar conversion ratio. That's something that we're going to get into. But for today, I wanted us to use the conversion factors that were given to us in this set of problems. And so we know that every 1H isotope atom weighs 1.0078 AMU. And that every AMU is a very small fraction of grams. Sarah? By the time we get to the end of next week, you'll be fine doing it whichever way you want. I just want to make sure that people are laying things out in a clear way. I'm assuming that people's work on these few problems are not going to look great, but if you work through and completed them, that will be worth credit for those problems for today. Eric?
Since you only have one hydrogen atom and you know how many
So let's keep going. Let's keep working through these. For this problem, I showed it this way because I want to be very rigorous and show the approach that I want you to use for all conversion problems. Okay? So then, what would be different about this problem? Talk to your neighbor. What would be different about the setup that we just showed for this problem? Can I hear a new voice? What would be different? We'll even pull up the last one that we just had. What would be different about this? Moab? The number of atoms. What would be different about it?
Well, carbon in the beginning, instead of doing 1 times the H1 atom, we'd be doing 12 times the C atom. As well as the atomic mass.
So careful, this is asking about the weight of one carbon-12 atom. Okay, so can we have someone maybe tweak what would be different about this starting point here? I get a new, yeah, Trey?
It would just be the same number of atoms, but you would change the AMU for that atom value.
Okay, so would we change what's here though?
Yeah, it would be.
Okay, so that's a really important distinction because that then dictates what conversion factors we can use. And then your point was that one carbon-12 atom doesn't weigh the same as a 1H atom. So we would do 12 AMU is every carbon-12 atom. What about this last part? Would this last part be the same or would that be different? Why would this be the same? What is this conversion factor being used to do? Hand raised? Tyler? Great. I want you to get in the habit of saying that each conversion factor, the reason we're using it is to convert from this unit to this unit. And even more specifically, to say we're going from the weight in AMU to the weight in grams, or the mass in AMU to the mass in grams. Because this one is not that, right? This one is from the number of them to how much they weigh. So the more detailed we can be in that description, the more obvious it's going to be why we're using the conversion factor steps the way that we are. So we would use the same thing there. Why did I use 12 AMU? So for carbon 12, it is the standard for what an AMU comes from. And we'll talk a bit about more about that in class today. But if we find a carbon 12 atom, that's what they defined as, well, it has 12 nuclear components, 6 protons, 6 neutrons. So we're going to say that every proton and every neutron weighs 1/12 of that. So that was kind of our definition of the scale. Joey? We'll get into that in a little bit. So if we're talking about carbon 12, we would use 12, exactly. But what's on the periodic table is not only carbon 12, it involves other isotopes as well. So then what would be different about this setup? Talk to your neighbor again. What would we do differently for the unit conversion approach for this process? New voice, please. New voice, volunteer. Eric.
Your unit that you were converting would be 4.35 times 10 to the 6th.
Okay, so we're going to go back to this, and instead of starting with one carbon 12 atom, I probably should have included. So we had everything here. So we would use this exact same setup. The only difference is we're not starting with one carbon 12 atom. So going back to your question, Eric, we know it's one carbon 12 atom. Like, why are we going to use this? This is why. I want you to see that if we change the number of them, we can identify, well, our starting quantity is different, but everything else is the same.
I was more talking about the number of the AMU. Since we know it's only one, there can't be any other isotopes, so it would be 1.0678 would be just one.
Ah, so this is not one exactly. It's a proton. It's only one proton. But kind of what, remember your name? Jackson was referring to earlier, is that the mass is actually slightly different from one, even though it only includes one proton. And so that has to do with the binding energy, which is what he was getting at. So if you want to read about it in Chapter 2, there's a section on binding energy. I highly encourage you to do it. It relates back to Einstein's equation of E equals mc squared. Those protons are being held together. It takes energy to do that, and that's a conversion of mass. And so it's pretty complicated. It's very interesting. Kind of blows your mind to think about the conversion between mass and energy. But that's why if we're doing 1H, we have to use this. Yeah?
Okay, so on this part, we only use like Avogadro's number. So this isn't the finished product, correct?
So we are not using Avogadro's number anywhere here yet. So we will be talking about that later today. But to answer the question that we just had with 4.35 times 10 to the 6th. We were only talking about how much do these weigh in grams. And so I think what you might be getting at is, so you guys, if you're comfortable with using moles, then we can start thinking about what does this mean in terms of grams per mole as well. And we'll be doing that over the next couple days, so you might be a step ahead. But for today, we're specifically focusing on AMU and how we go from the mass of one carbon atom, how that allows us to convert to other ones. Jackson, quick.
It's also worth noting that the mass of the proton and the neutron comes from the binding energy, mostly from the binding energy of those constituent particles.
True. Quick. What's that? Are we going to?
Do number 4?
Yes. So that is our next question. Before we go into question number 4, though, any questions on how we would do 3? Questions? So we know how many carbon atoms, so how do we convert from the number to how much they weigh?
I'm Josh.
Thanks, Josh.
Multiply it by the mass of one
Okay? Or another little bit more technical way to say that is use the conversion factor of the mass of one carbon-12 atom to convert from the number to how much they weigh. And then once we have the mass in AMU, we would use this conversion factor to go from the mass in AMU to the mass in grams. Okay. So then let's do... Is this question 4?
Yeah.
All right. So talk to your neighbor. What would be different? What would be the same? And I want you to calculate the final answer for this one. Go ahead and calculate the final answer. Compare your final answer if you've already calculated it. Another 30 seconds. Like writing it all out, conversion factors and all that stuff.
Oh, okay.
So,
There's wasn't very much wrong there.
Hey, I just put down 12. Is that okay?
12 would work because of the significance figure.
what are the units?
Oh, 12 grams, yes.
Depends on how many sig figs you use in the starting one, if you're saying it's exact or not. All right, so let's go ahead and, Natalie, are you willing to share how you did this? What's your starting quantity and how you work through it? Okay, you put that over 1. And then what conversion factors would you use to answer this question? Sure. Okay. And then, what was your last step? 24th, I think, right? Is there anything you might have missed? Okay. And so every time you're working through which one of these conversion factors you use, I really want you to say, I'm using this conversion factor because it lets me go from the number to the weight in AMU. Last conversion factor because it lets me go from AMU to grams. Okay? That's a really important part of this process. So can I get a volunteer for what answer you got for this? Love? Okay, pretty important part there.
Yeah, units.
So, wait. How does that make any sense?
Because
raising hands. Raising hands here from different voices today. All different voices. We've heard from a couple people a number of times today. Can we hear from new voices? New voices. Want to share with us what that means? Avery?
Because it's sig fig, 12 AMU, you can only have 2 places, so you round to the 12 grams.
Okay, true. So why does that 12 look kind of weird there? Savannah?
Should it be like 12 grams of carbon-12?
Okay, yes, so it is 12 grams of carbon-12. What do you notice about that 12? What stands out about the 12, Matthew?
The number of atoms creates the mass number in grams. The mass number in grams is equal to that many atoms of any element.
Okay, so maybe let's back it out one step. What's special about that number that we just started with? Sarah? Okay, so in this case, the amount of ANU is equal to the amount of grams, but with a specific number. What is special about that number? Kayla? Yes. So that number is Avogadro's number. So what chemists did, early chemists they said, we've been able to figure out that carbon has 12 nuclear components. And so if we have one of them, we're going to say they weigh 1 AMU. They were a little bit off, okay, due to the binding energy that we were discussing. So that means that one carbon atom weighs 12 AMU. But if we have 12 grams of it, let's just make our lives easy, and 12 grams of something that has 12 nuclear components, let's call that our special number. Our special number, the guy who found it was Amadeus Avogadro, so he named it Avogadro's number. And then he said, well, how many things do we have in the 12 grams? So that number isn't because they decided on this number. That number is because they said, in 12 grams of carbon-12, how many atoms are there? And it turns out it's that many. Is that a lot or a little?
That's a freaking lot.
10 to the 23rd. That's a billion, million, I think. So that's a number that they defined. And when we talk about things that are really small, the size of an atom, but we talk about them in physical quantity size, so maybe if this was all carbon-12, this would be about Avogadro's number worth of carbon atoms. So it's a way for us to kind of wrap our head around the quantities. We can talk about them in how many there are without talking about them in 6.022 times 10 to the 23rd of them. So this is called 1 mole. Is the same as 6.022 times 10 to the 23rd of anything. We could have a mole of people, we could have a mole of pennies, we could have a mole of carbon atoms, we could have a mole of anything. It's just a number of them.
Yeah, but it's an insanely large number.
It's an insanely large number. So the things are really small, we're going to count them in a unit. Like, we wouldn't count atoms in dozens. Because you have a dozen carbon atoms and they're still really small. So the mole is our way of kind of wrapping our head around really large numbers of things. If we had a mole of people, then the whole universe would be full, packed, elbow to elbow of people. So we're not going to talk about people in the terms of moles.
I don't think there'd be enough physical fundamental particles in the universe.
Probably not that either. Okay, so now we have a new conversion factor. So we could say 6.022 times 10 to the 23rd atoms of carbon-12 is also equal to 12 grams carbon-12. Or can we replace this with something easier to swallow?
1 mole.
And this is the conversion factor that you guys were using. And so I wanted to point out how we get to this conversion factor. So if I say a mole of something, you automatically think a very large number, specifically that number of things. And depending on how much those things weigh, we can get some insight, and the number at the bottom periodic table can be used for both. And so we'll get a little bit more into that. I think we've got to get scooting into the next section for that. So let's do that. Let's keep moving. I put this slide in here to remind myself. I have created practice problems in each chapter. I mentioned that earlier. So for OWL, go to all homework assignments, not the ones that are due because they're not due. You'll be able to see some practice problems from each of your chapters. I have recommended the book that these POGO activities come out of because there's a lot of activities we won't have time to do in class. But we're going to be doing this activity today and in class on Wednesday.
I looked up the book. It was $83. Is there anywhere you can get it?
Yeah, you can get it. You can rent it for like $17 on Amazon. You don't have to get a specific version of it or edition. It's the 6th edition is the one that I'm referencing as far as like the activities. It might be slightly different for older ones. So you should be able to buy it for under $40, I think, or $50. And you should be able, if anyone can find it, post it to the Canvas discussions for logistics. That would be great. All right. So we're going to start up on activity 2. So go ahead and grab the handout that Sam passed out. And I want you to read carefully through the beginning part and answer the first couple of questions. Do we have answers? Yes. Does anyone need one? Sam's got one. Great.
Does anybody else have one?
And while you're working on that, why don't you go ahead and pass activity 1 down this way towards Sam, towards the left side of the stage. Make sure your name and ID number are on it, please. I need to be able to identify it to you. All right, so to orient us to this, go ahead and click in your answer to the first one. I'll be handing these back on class on Wednesday. You can go ahead and talk to your neighbor if you can immediately answer this question. I need a couple more clicks. Once you answer the question, keep going through the rest of the questions. I'll ask for reports every once in a while. So where do we find to answer this first question? So at the bottom of the table, we can see that there's 3 isotopes, magnesium 24, 25, and 26. What's the same about those? Is that the next question? What's the same about each one of those? Kiana? Number of protons, that defines it as being magnesium. What's different about each one of those? Trippy? Trip-T, sorry.
They have a different number of neutrons and mass.
Great, they have a different number of neutrons. So why don't you go ahead and keep working through some of these problems.
use your conversion maybe to do that?
Should I?
I'll make the last question.
Don't worry about it. Yeah, I'll erase it afterwards because, yeah, I'm not too worried about that question.
But obviously I did. If you like, oh yeah. Like, can you put this paper in with this? Like, show something that it's written.
So this is for you to keep. So
Like
if
the
it's not
next
homework,
one.
yeah, for sure. Make sure to use your peers as resources. This is meant to be done with brainstorming in small groups. So let's go ahead and talk through a couple, just to make sure we're on the same page. If we were to see one carbon atom at random, which one do you think it would be and why? New voices? Heard number of people? New voice, new voice. Go ahead. What's the name again? Krush.
About 12 AMU because it's 98% abundant.
Is it about 12 AMU?
It is slightly more.
Kevin? 12 AMU. Why is it 12 and not slightly more than 12 or 12.011? Because if we go back to this first table, we look at what are the different isotopes of carbon. There's carbon 12 and carbon 13. The question asks, if we're to go in nature, which one are we more likely to find? Which one is there more of? Natural abundance on Earth. There's almost 99% of carbon 12, and then there's some carbon 13. And how much do they weigh? 12.0000, and the 13 weighs just slightly above 13. So if we're to go and pick a random carbon atom, we're not going to find 12.011. And then the next questions kind of get into that. So I saw a lot of people doing something fantastic. For question 4, what kind of approach should we be using to answer question 4? Dimensional analysis or unit conversion. I saw some people just writing out the answer or writing multiplications. I want to make sure this is exactly what we trained for. I want you to be showing me what's our starting quantity for question 4A. 1,000 carbon 12 atoms. How much does each carbon 12 atom weigh? And then using that to report your answer in either grams or AMU. Does it say? It says AMU. Okay. So make sure you write that all out. And then go ahead and click in your answer to question 5 when you answer 5. Just has those same options, but it has it written up on the board. It's multiple choice. Make sure to talk to a neighbor if you're not quite sure how to answer this. I didn't click the question 4 now.
Oh.
Did you guys come to an agreement in the group?
Yeah, we chose B instead of A.
If you've already finished this answer and clicked in, then keep working, please. I shouldn't see anyone sitting idle. There's tons and tons more to do in this packet.
I've learned the ways of the calculations. The Uruguay way.
Do you go on tomorrow?
All right, I'm going to close out on question 5. Who's right? Talk to your neighbor. I see a mix between A and B on question 5. Please talk to your neighbor. A and B are almost equally chosen for the question 5. And resubmit your answer when you're done. Try to find someone with a different answer than you if you had the same answer as everyone around you. Make sure to resubmit your answer to this question on the clickers. Resubmit your answer, resubmit your answer. Closing out. Okay. Did anyone change their answer from A to B and is willing to share why? Go ahead, Logan.
I changed mine because due to that there are still a percentage of carbon-13, it could throw the average if you have 1,000.
So if we choose 1,000, we're not going to get carbon-12 every time. If we did get carbon-12 every time, this would be the weight of 1,000 carbon-12 atoms. But every once in a while, about 1% of the time, we're going to get a carbon-13. So that means that it's going to be a little bit heavier because every carbon-13 weighs more. So we're going to end up with... So let me select the right answer. I guess not. We're going to end up with slightly more than 12,000 as the mass of all of those. And that is what Model 2 focuses on. So let's do this. You guys already have some pre-class homework for Wednesday. So why don't you just read through and just answer these 2 questions right here. That'll get us up to speed right when we start class on Wednesday. We were supposed to complete a lot more today, but we spent a lot of time on last class's homework. And did everyone see my announcement over the weekend? Yes. If you don't get Blackboard announcements, please make sure to change your settings. That's how I communicate anything important. What it said is that on the pre-class quizzes and the homework, you're graded on completion. That means if you don't get 100% on any part of a problem, you get 0%. Okay, that's really important to know how the system works. So if you get 80% on one of the sections for your pre-class quiz, that means you don't get any credit for it. Keep doing it until you learn how to do it. Come to office hours, post a discussion board, work on other things. Come see me after class if you have questions about that. These final pre-class quiz will end. Pre-class quiz
made a taller flimsy.
Yeah, I didn't even get one of the other people who didn't have one because, sorry. I grabbed them as a stack. It felt like
I
it.
saw it. It looked the exact same.
But your email definitely helped me with that, so I appreciate that.
Sitting there like last night, I was like, he told me.
Okay, I had an X6 morning and my key broke in my ignition.
Oh no.
So can I email my, don't worry, I left it on the table.